All right, we are going to be moving on. First things first here. Hope you enjoyed the day off. It turned out there wasn't really a lot of reason to have no school yesterday. People in Physics 252, because we weren't able to go over Gauss's law in class yesterday, I postponed the assignment that was initially due next Tuesday a week because we haven't gone over it. So just make sure we have that announcement clear. Also, a student contacted me about the concept coach questions. There's concept coach questions based on the material we're covering before each lecture. I had all of them for chapter 18 up before school started, and I put up the ones for chapter 19 through 22, I believe, yesterday on Moodle. You might notice, like I did, that there is a mismatch in the section numbers, that your schedule shows one more section in each chapter. And that's because the textbook went through and renumbered the sections, and then they renumbered them again. They put the introduction as, well, initially the introduction didn't have a section number. And so then they added the introduction as section 1 in each chapter, so it shifted everything forward one. And then they took the introduction and said, no, that didn't make any sense. Let's make that section 0 in each chapter. And so that's why the numbers are one off each time. You know, it shows one more section in the chapters than what there actually are. But the concept coach questions just follow the numbers in the guide, understanding that the last number for each chapter doesn't exist. We're going to talk about electric potential today, also known as voltage. But before we get to that, we have to finish up a few topics with electric field. So first, just a little problem to get us thinking about electric fields. A thin metallic spherical shell of radius r carries a total charge Q. So if it's, just an admission of my guilt, I accidentally overwrote your lecture, so I had to quickly put it back together, and I don't have the extra page, area underneath each page to do my work now. So I'm going to have to go to the next slide where I have the picture instead of scrolling down and doing it. But we have charges spread out evenly over the shell's outside surface. So I have a shell. Here's my shell. How is the charge going to be positioned on the shell? Okay. It's going to be on the outside, and it's going to be spherically symmetric. Why spherically symmetric? Because as we saw from the first day, the charge is trying to get as far away from all the other charges as possible. And so if I have a symmetric shape, that's going to result in it just spreading out. So I'm going to have, those are supposed to be plus signs all the way around. Charge equally spread out. Now, when I put those plus signs, what does that really mean? Lack of electrons. I didn't put positive charges on there. I took electrons off, and the electrons distributed themselves, so it's neutral everywhere except for on the surface where we have missing electrons to give it the positive charge. So there's my sketch of what it looks like. Now, the problem says to sketch the electric field outside. Well, what direction did you learn electric field goes? Toward or away from positive charge? Away. And I told you from the surface, what direction does the electric field line always point? Okay, normal in a two-dimensional picture that's perpendicular. So the electric field lines have to be going symmetrically out like that. I know it doesn't look good because of space. Well, that wasn't very hard. What about inside? That is the correct answer. Outside, it just looks like this. Inside, what would you do? You'd have all these things going away from the surface, normal to the surface. To maintain the spherical symmetry, they'd have to come together at the center. But the electric field lines start and end at charges or infinity. We can't have them all merge here at one point that's not a charge. And so logically, you are prone to say well, then we can't have an electric field, but that's not a real reason. So here's the real reason. Gauss, I cannot remember his full name. It's something like Carl Wilhelm or something. Gauss took the idea that we've already looked at. From one of your homework problems, you had to say, okay, if this is plus 2q or minus 2q, then what does plus 3q look like? And how did you decide if minus 2q looks like this, how do you decide what plus 3q looks like? What was your thinking there? Well, it was 3 halves because it was 2. But yes, that was the idea. That the number of electric field lines, the number of lines per space represents the strength, and the strength is proportional to the charge. And so Gauss said, you know what? If you give me a container and I measure how much electric field comes out of that container, I can tell you how much charge is enclosed. Because the electric field lines were proportional to, or the electric field strength was proportional to, the amount of charge enclosed. So Gauss came up with a law called Gauss's law, which for non-calculus purposes says the electric flux is equal to the charge enclosed over the permittivity of free space. Now, electric flux should mean nothing to you. Unless you've read ahead and you're a good student, it means nothing to you. What it means is the amount of electric field strength going through a surface. And so, not written, but meaning here, you have to have a closed surface, and the electric flux is equal to the sum over all pieces of the surface of the electric field dotted to the area. And of course, if we were in calculus class, what is that summation going to become? Integral. So in calculus, we draw it like this, or write it. Integral sign with the circle means it's over a closed surface. That surface means, or the circle means it's over a closed surface, no holes. And then it's electric field dotted to dA. dA is the area for each little piece. What direction do we assign for area? Because you see it's a vector. We assign the area as the direction normal to the surface. So if I look at my sphere, at every point on the exterior of the sphere, the dA is normal. So I'm going to have, the area is pointing like that. Now, what does a dot product mean? We're multiplying the parallel parts. So to take the flux on this surface, I say, okay, I have the area is parallel to the electric field. Based on my symmetry, and you see symmetry is a big part here, the electric field is always going to be parallel to the area for my sphere. And so that means this sum of electric field dotted to the area is simply the strength of the electric field at my surface times the total area of the surface. Now here's something that makes this a little more fun for us. The closed surface is not necessarily a physical surface. It's a surface we use for calculation. So if I want to find the electric field at a radius r, all I do is I say, let us imagine that there is a spherical surface out here, a radius r away from the center of the sphere. Everybody with me? Okay? So if I have that, then the electric field, I don't know the strength of the electric field there, right? That's what I want to find. But I can calculate the area because the area for a sphere is 4 pi times the radius squared. And so that means the flux on that surface is equal to whatever that electric field is times 4 pi radius squared. And remember, based on our symmetry, I had to use a spherical shell so that it matched the symmetry and the electric field was parallel to the area at all points. So that's my flux. And then according to Gauss's law, that flux is equal to the charge enclosed. So how much charge was enclosed in this problem? They told us charge Q. And so that's going to be equal to the charge enclosed Q over epsilon 0. So if I want to solve that for my electric field, I just divide everything by 4 pi r squared. I have the electric field is equal to Q over 4 pi epsilon naught r squared. Now I rearranged it a little because we defined K, constant K, as K was 1 over 4 pi epsilon 0. And so this is the same as E is equal to KQ over R squared. You've seen that equation. That was the equation for the strength of the electric field due to a point charge. So what we see here from this Gauss's law calculation is if I have a symmetrical distribution, right? I only could do this for the symmetrical distribution so my electric field was parallel to the area. Then the electric field is the same as if I'd had all the charge right at the center of the sphere. So that's an interesting outcome. Now let's go a step further with this Gauss's law idea. What if I made my Gaussian surface, my imaginary surface that I want to calculate the electric field on, at some point inside of my conductor? What can you tell me about the conditions inside the conductor? The what? The electric field is 0 inside the conductor. So in this case, what's the flux going through that surface? Has to be 0. And so if the flux going through the black surface is 0, how much charge is enclosed? If this equation is true, then the charge enclosed has to be 0, which means how much charge do I have on the inside of this surface? None. Now, if I'd had a charge in the center here, let's say I'd put a charge here, and that was, let's say, plus 5 coulombs, then what would I have on the inside surface? I'd have to have then minus 5, so the total charge enclosed was 0. But we didn't have a charge there. And then finally, let's say I want to find the electric field inside here. So there's my Gaussian surface, my surface I'm going to calculate the flux on. How much charge is enclosed? 0. If the charge enclosed is 0, what does the electric flux have to be? 0. And if we have spherical symmetry, we know the electric field has to be either in or out, always normal to the surface, so the same direction as the area, which then requires that the electric field would have to be 0. So Gauss's law gives us a reason for the electric field inside to be 0. Now, the entire class yesterday was going to be covering that, so you Physics 252 people know what to look forward to next week. For Physics 152 people, that's the end of our Gauss's law discussion. What's important to understand about Gauss's law, let me write Gauss. A lot of people see it and pronounce it wrong. It's Gauss. I've heard people say Gauss, but it's Gauss. Make sure we're clear on that. Yeah.
So basically, it's the same as if there were like a spherical shell, and we were talking about the gravitational force, right?
It works exactly the same with gravitational force, yes. So you can actually use Gauss's law for gravitation as well. Okay, so what's important about Gauss's law is it sets the relationship between the electric field and the charge enclosed. And the flux is only going to depend on the charge enclosed. So you can do goofy-ish things, like say, okay, I have a cube with charge, and I'm going to make a Gaussian surface out here. That's not a real surface, it's a surface I'm calculating the flux on. How much charge is enclosed by my Gaussian surface? None. So that means the electric flux has to be 0. But in this case, I don't have the symmetry that my electric field is always normal to the surface. And so calculating the actual distribution of the electric field is hard, but we do know that the total flux has to be 0. And so oftentimes we'll have questions like, instead of this, we'll take a point charge and put the point charge in the center of a cube like this. So there's a point charge in the center of the cube. And it asks how much flux goes through, and if it's at the center, then you have it somewhat symmetric in terms of the faces. How much flux goes through each surface? Well, there's an easy way and a hard way. The easy way is to say, well, the total flux has to be the charge enclosed over epsilon 0. And since there are 6 symmetrically equivalent surfaces, the flux for one surface is 1/6 of Q over E0, or epsilon 0. Right? That's quick and easy. That's if you understand conceptually what's going on. If you just try to brute force it, you say, okay, well, I know the electric field vector has a magnitude of kq over r squared and a direction that's going out of the charge, and then I can calculate E dot dA over the surface and integrate in 2 dimensions, and you'll get the same answer, just with a whole lot more work. We try to avoid that work, so we try to think through Gauss's law. So, for instance, the Physics 252 students, that's physics with calculus, every time they use Gauss's law, almost every time they use Gauss's law, I shouldn't say every time, they're not going to use any calculus. They're going to choose a shape to match the symmetry, and based on that shape, then they can do the calculus without ever having to do any calculus, just by symmetry arguments. Looking forward to it, aren't you, folks? That's the other problems on that assignment, or Gauss's law. Okay, and this is just a fun picture. Electric eels, I think they produce about 600 volts. That's kind of scary, right? And they actually, you have animals like bats that use echolocation. They send out a chirp and they listen for the return, and they use that to navigate. The electric eels actually put out a small voltage, like 10 volts or less, and they feel the fluctuations in the electric field produced by that to help them navigate around objects, which is totally cool. And then when they get scared, they ramp it up and they shock the bejesus out of anything, which is bad. Okay, so let's get talking about the electric potential. So the first thing for understanding electric potential is going to be to talk about a parallel plate capacitor. Capacitors come in a different chapter. So we have like this equation. The electric field between 2 parallel plates where you have plus Q on one side and minus Q on the other is Q over epsilon naught area. Later on, we'll be able to calculate that and derive it. Right now, we're just taking it as this is an equation we will derive later to tell us how the electric field between the plates relates to the charge on each plate. What's the point? You can make a uniform electric field between the 2 plates. Now, if I have this uniform electric field, and let's say that I just put a little charge right here, and so let's make that an electron. So it has a negative charge. What is an electron going to do if I place it there between those 2 plates? There are 2 easy ways to analyze an answer.
Go towards the positive plate because opposite charges attract.
Okay, it's going to be accelerated toward the positive plate because opposites attract, so negatives attract to positive. Also, likes repel, so it's being repelled from the negative. So that's one of the 2 easy ways. Does anybody see the other easy way? The other easy way is the one that is on the screen. It's going to feel a force due to the electric field that is, force is equal to QE. So the electric field is pointing to your left. And since the electric field is pointing to the left and it's a negative charge, then the force is in the negative left direction or to the right toward the positive charge. And since the force is QE, and Newton's second law says the sum of the forces is equal to mass times acceleration, assuming gravitational force is negligible, then the sum of the forces is just this electric force, and we get the acceleration is QE over m. So we can determine the acceleration based on the electric field. And you can see it's a lot easier, since it's a uniform electric field, it's a lot easier to do the acceleration this way than to say, well, I have a force of, and calculate the force between that negative and the entire positive wall, calculate the force between that negative and the entire negative wall, add those up, and then divide by m is a harder job. So the first and most obvious way that Jonathan answered, right, it is the most obvious, it's the way I would have answered, is harder calculationally. Whereas using the electric field makes it a much simpler calculation. That's why we use fields. We use the fields to make the calculations simpler for us. At first, it doesn't look simpler. But when you start getting to problems like this, you say, yes, much easier than having to do calculus and integrating over a whole bunch of charges. So if I have this charge in here, and it's going to have a force, and it moves, what do we call it when we have a force and it moves due to that force?
Acceleration.
Well, we do have acceleration because it changes velocity, but I'm looking at specifically a force and motion. Work. We're going to have work because work is defined as work is equal to, I'm just going to put the generalist of all, force dot delta x. And so we know what the force is based on force is equal to QE. And then if I multiply that by delta x, that would tell me how much work. So I can calculate how much work is done to move the charge from here to here. And if there's work done on what's going to happen to its kinetic energy? It's going to change because we're going to have the net work is equal to the change in kinetic energy. So then we can calculate what's final speed is going to be based on that work. Now, let's move right past that. Everything that I've been talking about here actually can work with gravity. We didn't do it with gravity because gravity was simple enough if you're on the surface of the earth that it's not worth our time. If you do something that's not just on the surface of the earth, these ideas do become useful in working with gravity. So the charge is going to lower potential energy. Right? That work is taken to lower potential energy. And that is a fundamental rule in physics. If I just let something go, let this ball go, it's going to go to the lower potential energy position, which for gravity is down. For charge, if it's a negative charge, is it going to be lower potential energy going toward positive or going toward negative? Negative charges can have lower potential energy going to positive. What about positive charge? Will it have lower potential energy going to positive or negative? Negative. So a positive charge will go to negative, a negative charge will go to positive, but both are going to lower potential energy. So the potential energy idea is a useful idea to help us understand how things should move. So, the question I just asked. What direction does a charge move? And when it says energy, that should be potential. Okay. Everyone's answered. We had 19 that said toward lower and 2 that said toward higher. I'm not going to go to having a student answer this. I just said this. So 19 people got the words I just said. Always goes to lower potential energy. That's, another way of talking about the second law of thermodynamics. It's always going toward lower potential energy. Nobody answers C or D. Why not? What have I said about voltage? Nothing. Hence, you probably assume, well, that's probably not the right answers. And you were correct. This here, I'm actually going to change over. It's just a fun, it's useful, but change sesame. But for my teaching purposes, it's fun. Come on. Yeah. These switches sometimes just fail.